Welcome back for a sixth presentation on Arduino exploration. We're gonna speed up things up as we're coming closer towards the trip to the UK, which is upcoming in April. So let's have a look for this presentation, what we got in hand. So we're gonna look into serial port and serial monitoring and why we need it, how it can help us, how it can prove our work, and what to expect from it and why we use it in general. Then we're gonna do a quick experiment in the potentiometer experiment. It's gonna demonstrate what serial monitor can do for us. The potentiometer is also known as variable resistor, and what it does by twisting the knob, we're increasing and decreasing the resistance to the board or to a component we are trying to control. We're going to look at the code and what's the new variables that we're going to add. And then we're going to do a control of an LED with the variable resistor or potentiometer. It's a bit easier to say variable resistor, so I'm going to refer to potentiometer as a variable resistor. And a quick schematic so you can follow the guide and follow what we're doing. Then we're going to break down the code and see what we have here, and we're going to have also a new function which is a map, and we're going to explain to you what the map does. Then we're going to look at converting signal to voltage. So how can we convert a reading of the variable resistor into voltage reading, so it's a bit more pleasant to the eye and easier to understand what we're actually doing with it. And we're going to introduce the float as well variable, which we're going to be using with the serial monitor and the variable resistor, and we'll explain the code, and that will be it for this presentation. So looking into the serial port, we already had a look at the potential of the serial monitor and how it can be helpful to us. Now let's have a look how changing the code can improve the serial monitor readings. For the next couple of the experiments, we'll be using analog ports, and this is the reason because as I explained before, when we use external components such as LED lights, they only give an output. We cannot really control them. We can switch them on, or we can do interesting stuff with it by using a code. However, when we use a variable resistor, what we do by twisting the knob, we're actually putting an input to the system, and that's why we need the analog pins for it, because we are doing and changing the input, and the input is changing constantly, so the program, the software doesn't have a code which says at this stage the voltage is going to be that. We can change it at any time, and that's why the analog is so important. So let's have a look at the potentiometer experiment. For this simple experiment, we'll need the breadboard, the wires, the variable resistor itself, and the Arduino. It's quite simple. When you look at the potentiometer or the variable resistor, you'll see there's two legs in behind and one leg at the front. The two legs behind is for the ground and the V5, the voltage, and the front leg is for the port itself, the pin. In my experiments, I'll be using the pin AO, which is the A0, and by the way, when you connected the ground and the V5, it doesn't matter which leg you connect it to. All it's gonna do is just gonna reverse the results. So if you get, let's say, a 0 to 1023 when you twist it from right to left, if you switch it, you're gonna get a 0 to 1023 when you twist it from left to right. So it really doesn't matter which way you do it. There's no set like the LED light, one leg bigger, one leg shorter. So just do it the way you want. and we're gonna look at the code as well now. So the code is quite simple. We have the serial begin 9600. This is the open communication serial port, so we can actually take a reading from our Arduino. Then we have the void loop, and within the void loop we have nothing else in the setup. Then the void loop, it actually sets an integer into the sensor value equals analog read. So what we're saying, the sensor value will equal analog read A0 or A0. And then the function is pretty simple, serial print in, so we're saying to the code, print the output of the sensor value with a delay of 1 second. Why we do not declare a variable as, let's say, int potentiometer as equals A0, this is really no need because we already interpret sensor value, and the Arduino is quite smart and it already knows that within the analog, the Arduino is quite smart and already knows it doesn't need an interpretation of what is being connected to it. And so let's have a look at the code and how it works. So I've already set up my Arduino and I've already uploaded to my Arduino, so it's all working. I'll just verify it one more time just to be sure I have the correct code here. As you can see it, I've done it with the interpretation of the potentiometer at the top, so I set it and then I'll upload it to the Arduino. It's all uploaded completely fine, and then we go into our tools and serial monitor, or you can use Control Shift M. And then we're starting getting some values. So if I twist it all the way to the right, is some maximum value. As you can see, every millisecond, the Arduino is actually reading what's the position of the potentiometer, and then as I twist it to the left, the value changes, and it changes quite rapidly. And going all the way to the left, it will go to 0. So what we're doing here, as I said, we're pretty much just increasing and decreasing the resistance, and we're getting a value when we do that. Let's have a look. Let's try and re-upload the code the way it is done in the presentation. So I'll just take the interpretation of the potentiometer. It will still verify it absolutely fine. It will still upload it as it did before. And then I'll just use the shortcut to open the serial monitor. And again, it's reading the values. As I said, you don't need to define the potentiometer. So perfectly, it works fine. Why we have such a small delay here? We have a 1 millisecond delay. This is because if we don't have a delay within the actual program, it's just so much data will be jumping out and it's overloading the serial port. There's no need for it. We do need to give it a little bit, a split second time to be able to write a new value, otherwise it will be way too quick. So how the last experiment was quite straightforward and quite simple. We used the analog pin because we do have an input from ourselves, from the environment, and that's why we need to use the analog pin. It's not a straightforward digital on or off. So let's try a bit more complex experiment, this time controlling an LED with the potentiometer. For this experiment you will need Arduino, breadboard, the wires, potentiometer, an LED, and again a 220 ohm resistor. This is the schematic how you will connect it. So for the potentiometer it will be exactly the same. Both legs are used on the same horizontal I used for ground and V5. The single leg is used for the actual pin itself, which is A0 in my case, or A0. If you have by any chance a potentiometer with 3 legs in one line, then what you'll have to do is the 2 outer legs will be used plus minus, and the middle one will be used for the actual pin. And then the LED light will connect the longer leg, the plus leg, into a 220 ohm resistor, and then from the resistor we'll connect a wire into the slot of pin 9 in my case, and then from the shorter leg we'll have wires going into the ground as well. And now let's have a look at the code. So here we do have to define analog pin, analog out pin. We need to set values for the sensors to begin with. Otherwise, it's just good practice as well. When we define the sensor value and output value is 0, then we'll have to set up the serial to begin at 9600, which is a standard bandwidth. And in the void loop we'll have sensor value equals to analog read, analog pin, in pin. So the sensor value reads the pin, and then we have output value, and here we have the function of map. So this is a very interesting function, and what we do with the map is we take one set of values, we can see here from 0 to 1023, and then we map it into another set of values. It's quite important because here we are working with pulse width modulation. Again, this is one of the best practices to be able to dim the light in a live state. We'll have to convert those values. Otherwise, what we're gonna run into is that because pulse width modulation can only take 255 value, which is the maximum, and if we don't map it, then our potentiometer is not going to be working to the full in a sense. Then we're going to do an analog write, analog out pin, which is our pin number 9 output value, and then we'll print the results into the serial port. So let's have a look, and again we do have a delay of 2 seconds this time. Let's have a look at the code, and we'll upload it to the Arduino here. So the code verified itself correctly. Now is the upload stage. The Arduino has accepted it, and then I'll do the shortcut to the serial monitor. So now what we did in the code, as you can see, first of all we set up a, let's say, we'll call it a bit of text, so otherwise we would have seen just 2 different numbers jumping out at us. So in the serial print we said the first one sensor equals to, do make sure you have the double quotation on either side. This means that we are just dealing with text which we want to print out rather than a value which we are taking from somewhere. Then we set into that sensor equals the sensor value, and the sensor value is read by analog read, analog in pin, which is AO. And the third function is serial print. So what we wanted to print, the /t gives us a space, and then the output equals to, again with double quotation on either side, to tell the Arduino this is a text only, it's not a value which we're trying to read. And the last one is print in output value, an output value of the actual sensor itself. So I'm just going to twist the knob now. It's on the 0 position, and as I'm twisting it I can see that there's a change, and as you can see each value is corresponding to the mapping. So you see that the maximum we can go to, 1023, will be equal to 255 output value. And on the board itself, you'll see that as you twist the knob as well, that the actual LED light will become brighter and brighter, and if we go the other way around, it will dim down until it switches off. But you can see how the mapping correlates to the actual values. So we can see that, let's say halfway through, which is going to be 500 and just about 12. Let's see if we can get it there. Oh, just missed it. It's quite hard to get it spot on. Let's say 20. It corresponds to roughly the halfway through of the actual 255. It's a very useful technique when we need to map and work with a input of an analog and output of pulse width modulation, in a sense. Just coming back a little to the map function. We set up the output value to equal map. So how we use the map function? Obviously we have the keyword, which is a map, all small letters, and then we have the brackets. And what we do here, we want to map the sensor value, which is the analog read, and then we define the sensor values from minimum to maximum, and then we tell the function what we want to map it into from the minimum value to the maximum. That's how you use the function. You always define what you're mapping, which values you're mapping, and what values you want to map it into. And as I said, it has to be in that order. So I hope that was quite clear. Do experiment with the code if you feel like it. It will give you just an idea what everything does, especially in the serial print, but for this experiment I will show a couple of different variations and we'll see the output results and what they do. So now we want to have a look at converting a signal to voltage. We can also convert the signal, the figure between 0 and 1023 to a voltage value, so then we can define how much voltage is going through our system. However, it is a little bit more tricky and we must then introduce something called float. Float is a data type which deals with decimal points, because if you can imagine, when we try, for example, let's say map between 0 and 1023 to something between 0 and 5, it will be quite a lot of errors due to the large amount we're trying to compact into such a small range of numbers. So for that we need a float, and the float, what it does, it allows us to actually use decimal points, where a int function where we define and store values does not usually deal with decimal places. It is a better approach to convert the signal to voltage because the difference is so high as well. So as we mentioned, when you try to take such a large amount of numbers and compact it to such a small range of numbers, you will have errors, in the sense that, for example, when let's say the figure between 0 and 250 will still might display to you as 0 volts. Sorry, it will be about 200. Between 0 and 200 it will still display 0 volts because the difference between the scales is so large. So let's have a look at the next experiment, the float serial monitor. We'll go back to basics as the first experiment. We'll just need the Arduino, the breadboard, the wires, and the potentiometer or the variable resistor. Same rules will apply here as connecting it in the first one. The code itself, again, we don't need to define the actual potentiometer because we're not storing values here. As we saw in the previous experiment, when we defined the potentiometer, it's because we stored the value. Here we're just printing a value out through the serial monitor so we can see what's happening within the system itself. Then we have the void setup, again serial begin 9600. Without it we won't be able to monitor through the serial monitor anything. Then we have the void loop, which is again running forever. We do say a sensor value, an integer sensor value equals to analog read A0, and then we introduce the float, and the float says the float voltage will equal to a formula, and this is a formula which was taken from the internet. It's not something that we usually come up with when it comes to converting or mapping numbers. It's not something that you have to think about. It's something that's already been done for you, and it's just a matter of Googling it and finding the right formula for what you need. You'll find that as you get more into the projects, a lot of it already has been done, and there's no need to invent something new here. So what we're gonna say, the float of the voltage, so we're saying the voltage can be in decimal places now, will equal to the sensor value times brackets 5, because we're using 5 volts, divided by 1023, close brackets. And then what we're gonna do, we're gonna serial print the sensor again, serial print sensor value into the sensor equals, serial print again /t will give you a space between the two, voltage equals to serial print in a voltage. So let's have a look how it looks in the code itself. I did play around with it, so I did delete the T. There we go. No V there. Voltage here. Yes, so just verifying the code again and uploading it to the board and just using the quick shortcut. And now we can see the potentiometer is in the left hand side, so in the 0 state. Again, it doesn't matter, you might have the Y's all the way around, which will just have a different state. And as we twist it, now we can see that the corresponding value 48 is equals to 0.23. If we didn't have that float, what will happen, we'll see sensor value equals 48, voltage will equal 0. And as we twist it, we can see the value increasement. So now we mapped the 1023 into the range of 0 and 5. And all the way to 1023, 5 volts. So that is pretty much what we wanted to cover in this lesson. We just do a quick variation of where we, for example, let's take out the T. And as I said, what we're gonna have just some mushed up results which are not pleasant to read to the eye, and hence it's better to use the T as a separator between the two readings. And that's what you have here, so which is not great. It's all together and it's not easy to read. So I do encourage you to play around with the code, and thank you very much for joining for those 3 experiments. We will be introducing more and more complex systems as we go along. The next 2 lessons, which are going to be pretty short, however, they're just going to cover some basics about the shields in more depth and about outbreaks, which like breakboards, mini breakboards, which can be used with your projects, and we'll explain how they can enhance your projects and what sort of functionality they can provide. Thank you very much for listening.